In this video, we're going to answer a fundamental question, and that is, do all reactions go to completion? Now, the reason we're asking this question is because up until this point, that has been the assumption that we have made. The assumption we've made has been that every time we had to do a stoichiometry calculation, we were going to use all of the reactant concentration that we were given. And we can kind of figure out that that's not always going to be the case. Sometimes we're going to have to figure out what is going to run out first. So we take a simple example like this. Let's say we have charcoal burning. We've got carbon reacting with oxygen to make carbon dioxide. Now, we can easily think of an example where I have charcoal and I lay it out in a barrel and I set it on fire. And after a while, all of the charcoal burns away. Well, why did that happen? Well, that was because there was plenty of oxygen around to get that charcoal to ignite and to stay ignited and to completely get used up. If I took that same charcoal brick, lit it on fire, and then put it into a jar and closed the jar up, I know from experience that the charcoal would eventually go out. And the reason why is that inside the jar there's a limited amount of oxygen, and the oxygen supply would eventually run out, and we would be unable to produce all of the carbon dioxide that was possible given the amount of carbon that's present. And so that's kind of the general idea that happens in the whole concept of a limiting reactant. So let's throw out some terms here. When we talk about a limiting reactant, we're talking about a substance that ultimately limits the amount of product that can be made. A good way to think about a limiting reactant is this is the substance that runs out first. So a limiting reactant is the substance that runs out first. And once the limiting reactant runs out, there's an excess reactant. And these are the substance or substances that remain after the reaction is over. And so with a limiting reactant and an excess reactant, we inevitably will have something that is left over. That isn't the case if we have a stoichiometric amount. A stoichiometric amount implies and is when we have exactly what we need. So I measure out the exact amount of carbon, I measure out the exact amount of oxygen required to react with that carbon, and they both run out at the same time. Another way of thinking about this is all substances are limiting reactants in this scenario. They all run out. They all run out at the same time. So this can be kind of difficult to think about, especially if you're starting to get into more complicated chemical examples. I want to give you something that you can kind of latch on to, though. So let's just envision a really simple scenario. Wendy's is selling cheeseburgers, and they're having a little bit of a shortage. So when they sell their cheeseburgers, they are only making them in this way. And so their recipe for a cheeseburger in the shortage of supply that they have in their kitchens, that every cheeseburger has a bun, every cheeseburger has a quarter-pound patty. So it's a quarter pounder essentially. Every cheeseburger has a slice of cheese, and it has 2 pickles, and it has 3 onions on it. So if this is the case, and this is our recipe, how many cheeseburgers could Wendy's make if this was the amount of food that they had on hand? And so I want you to think about that. I'm going to pause the video here, come back in just about 10-15 seconds. If you want to think about it, write out your answer here. Pause the video now and When we come back, we'll have the answer ready. So about 15 seconds. Okay, so we're back now. Got the answer? Let's see how you did. Well, the way that we would answer this question is we could take each one of those ingredients and figure out how many burgers I could make with each one of those ingredients. So my 13 buns, well, that can make 13 burgers. My 5 pounds of meat times 4 burgers per pound, since each burger is a quarter pound, that would be 20 burgers. My 25 slices of cheese can make 25 burgers. My 100 pickles could make 50 burgers. My 30 onions could make 10 burgers. And so, with each of these ingredients and the way that they're set out in mind, we really only can make 10 burgers. Because after that, we run out of onions, and while technically speaking, what is left over would be, in many people's minds, still a burger, it's not the burger that we were being sold. And so in this example, onions are the limiting reactant. Once the onions are gone, I can no longer make burgers. And buns, meat, cheese, and pickles are all present and in excess. So if we think about it from this kind of scenario, how do we apply this to chemistry? Well, it's simple. If I don't know which ingredient is the excess, I can do the same kind of thing. I can take each ingredient, use stoichiometry to figure out what amount of product each reactant will make, and whichever one makes the least amount of product, that tells us the limiting reactant, and the amount of product that they made is our yield. So this kind of approach to limiting reactants is a really common one, and it's a really easy one to kind of follow along. So this is the approach that you would want to take. And so let's look at the next example. If I have a 31.5 gram brick of charcoal and I burn it in an atmosphere of 102 grams of oxygen, how much carbon dioxide would we stand to make? Well, to answer that question, we need to take each of these 31.5 grams of charcoal and turn that into carbon dioxide. The 102 grams of oxygen, turn that into carbon dioxide. Comparing these two will allow us to answer the question of how much carbon dioxide is made. So in our first set, we're going to start with the 31.5 grams of carbon. And molar mass of carbon, 12.01 grams. In 1 mole. And our balanced chemical equation says that 1 mole of carbon will produce 1 mole of carbon dioxide. And 1 mole of carbon dioxide will produce 44.01 grams of carbon dioxide. And so if I follow those calculations all the way through, 31.5 times 44.01 divided by 12.01, I get that this particular reaction will give me 115 grams of carbon dioxide. Now, I don't know if that's the correct answer yet. I still haven't figured out if this is the limiting reactant, but I at least have something to work on and compare against. Now I need to look at the other reactant. I have 102 grams of oxygen. And I'm going to go through the exact same process. Convert the grams of oxygen into moles. So 32 grams of oxygen and 1 mole of oxygen. My mole-to-mole ratio here also 1 to 1. 1 mole of oxygen corresponds to 1 mole of carbon dioxide. And 1 mole of carbon dioxide corresponds to 44.01 grams. So I put that into my calculator. 102 times 44.01 divided by 32. And I get 140 even 140 grams of carbon dioxide. So in this particular circumstance, my carbon is the limiting reactant, and my oxygen is in excess. And that my theoretical yield is 115 grams of carbon dioxide. So I can automatically, based on these calculations, I can disregard this calculation here because it is more than this. Now, one really important note here. You have to, when you're doing limiting reactant calculations, you have to compare things that are alike. So it's not good enough to just compare moles of oxygen to moles of carbon. It's not good enough to just compare grams to grams if the things are different. So I can't just look at this and go, oh, well, carbon's going to be the limiting reactant because it's got fewer grams. I have to go through the process. I have to compare things that are alike in not only unit, but substance as well. That's a really important part. Let's look at one more example. Here's an example using acetylene. Now, I'm going to turn this over to you, and just like we did before, go ahead, pause the video, and try to work this out on your own. I'm going to post the answer here in just a couple of seconds. So if you want to work this out on your own, pause the video now, and we'll come back in just a few seconds. Okay, we're back. Let's see how you did. So the first part here was you had to balance the chemical equation. And then once you did, it fell into kind of the same pattern that we saw in the previous example. Now the main difference is that we were working with acetylene and it wasn't 1 to 1 to 1, but in the end we can see that the acetylene produced far less carbon dioxide than the oxygen did, so therefore it's the limiting reactant. The oxygen is in excess, and this becomes our theoretical yield. If you want more practice problems and examples, please look at these videos here in the description. Have a good afternoon.